Hello everybody, Greg is here. Sorry for not recording for a while. I hope I'll compensate with this video, which probably will be a bit longer than usual. And I want to talk about a mechanism of hydrogen splitting by frustrated Lewis pairs. I had a video about FLPs a year or two ago, and since then there was some developments, and also I wanted to understand myself the mechanism of this very interesting reaction a bit better, and I discovered a lot of interesting things which I will be happy to share with you today. So, frustrated Lewis pair, it's a Lewis acid and a Lewis base which cannot reach each other. That's why they called frustrated. The regular Lewis pair is a molecule which has an electron pair, that's Lewis base, and the molecule that can accept this Lewis pair, which has an empty orbital, is a Lewis acid. And when they're small enough, there's no problem, they just react and the bond forms between them. However, if you increase those side groups on both molecules to the extent this bond cannot be formed for steric reasons, you don't expect any reaction to happen. And indeed, no reaction happens. However, if you add a small molecule in a solution that can enter this space between the big Lewis base and the big Lewis acid, something does happen. So, for example, with hydrogen, the hydrogen-hydrogen bond is getting split in the way it shows here. So you get a cation and an anion. And this was extremely surprising at the time when it was discovered, especially because, let's say, if you add hydrogen to just the base separately or just to the acid separately, nothing happens. However, if they're both together and you add the hydrogen, then it tears apart. And hydrogen-hydrogen bond is relatively strong. So the first idea of the mechanism was proposed by the scientist who discovered this beautiful reaction, Douglas Stephan. He published this idea in the paper in JACS. The first paper was published in Science. And by the way, in this publication in JACS in 21, you can read a review about the reactivity of the frustrated Lewis pairs with hydrogen and the use of this reaction. The mechanism that Doug and his team proposed was a stepwise reaction. So first there's an interaction of the hydrogen with the acid, and such weak interactions were known. And then the base attacks the polarized hydrogen atom and then it splits. That was the first idea. However, a year later, theoretical chemists came into the picture, and all this video will be about those studies of theoretical chemists and their arguments with each other. The first group that studied this reaction on the theoretical level was the group of Professor Papai from Hungary, and they immediately found something very interesting. They found that there is actually some level of interaction between the base and the acid in the solution. So they found that they actually form a weak complex, even at room temperature. So the interaction happens between the side groups, which are bulky, of those molecules. So first, a few words about this complex that they discovered. This complex was not observed, and it was still, till now, it was not observed in the solution. It's still a theoretical concept, which is already very intriguing, because what's going on? Why you cannot observe it? They calculated that the association energy is pretty high. It's about half of the interaction for classical Lewis adducts. Also, they saw that no charge transfer occurs in this complex. So there's actually not any electron transfer between the centers here at this point. But then hydrogen comes. So when the hydrogen comes in the picture, there is an electron transfer from the base to the hydrogen and from the hydrogen to the acid. And then that's the way the hydrogen-hydrogen bond splits, and then it can be transferred to another molecule. So that's in a glance the first publication, maybe just another nice idea which was mentioned there. So the reason for such a reactivity, one of the reasons for such reactivity that the authors described, is that yes, they cannot reach each other, the base and the acid, and that's what makes them higher in energy. So, and that's why they react much better than any classical Lewis base and Lewis acid, which are in a complex, obviously, because there is less activation energy. And it seems like it's something obvious, but I remind you, before 2006, No one thought to do this, although it's so obvious. So probably it was not that obvious. And with frustrated radical pairs, this idea was not yet proposed at all. Anyway, the idea of increasing the side groups on two reactive molecules, not necessarily acid and base, can be a good idea to discover some interesting chemical reactivity. Okay, so very good. We have a mechanism that was proven by theoretical calculations, but it's never that simple. After 2 years, 2010, another theoretical chemist group, a collaboration between two German chemists, Grimme and Erker, they published another mechanistic study. You see, it's mechanism revisited. So they studied similar Lewis pair, like Papai's group, but they also studied another one, which is connected with the bridge here. And by the way, this hydrogen is a mistake, and it's too bad that the reviewers and the authors didn't notice it, and seems a bit weird, and there's other weird things in this publication. The hydrogen should not be here. So they say that according to the mechanism that Papai's group proposed, this reaction cannot work. But it actually works according to their calculation and according to experimental results that were published by another group. And they propose actually an alternative thing. They agree that there is a precomplexation between the acid and the base through the side groups. They also draw a line between the Lewis and the base, which apply on another interaction. And what is this interaction? That between Lewis acid and Lewis base, in this precomplexation, there is an electric field, because both molecules are polarized, and the energy of this electric field is actually enough to tear the dihydrogen apart. And they say that they actually don't need this electron transfer mechanism that Papai's group proposed. So this one. And I'll give a few citations so you understand what the actual drama that they try to make in this paper. Okay, so they say Papai et al. Have presented the notion that the HH bond is cleaved by such system, the associated Lewis acid and Lewis base, in an almost linear PHH-BRA arrangement, like in the transition state. We have now found that this proposal is probably a gross oversimplification of the mechanistic course taken, because the theoretical treatment used did not adequately take into account the interaction between the large substituents that are specifically used. And again, remind you, those guys are all theoretical chemists, and so they all care about their models. They all care about the way they calculate certain interactions and certain electronic arrangements in molecules. There is one strange thing in this statement. So I read Papai's paper, and they don't say that this linear arrangement is really necessary. I mean, on their pictures you see the almost linear arrangement, but it's not something that they say is absolutely required for the reaction to occur. So I don't know why they blame them for being inaccurate here. So basically, I think the bottom line, what they discovered, yes, maybe they didn't really take into account certain interaction between the side groups. Okay, so the next thing they write: we present the results of our state-of-the-art calculations for this problem, which has resulted in a more realistic description of the transition state involved, which features a non-linear. Okay, we understood that. And the basic message is that there is no need to involve specific FLP H2 orbitals. So this goes completely against my logic, my knowledge of chemistry. Like, chemical reaction always should involve some orbitals. But okay, and they finish with this statement: this study also shows that sometimes a rather accurate quantum chemical treatment is required to qualitatively obtain the right answer. And that's a bit offensive. So you start feeling the drama, right? So anyway, bottom line, we now have some argument which needs to be resolved. Professor Papai responded within 3 years in a big publication in JACS. So that's the graphical abstract. So he presents, that's the original model, the electron transfer model involving molecular orbitals, and the electric field model, which states that the electric field tears apart the bond between the two hydrogens. So let's see what he writes. The electric field-based reactivity model, consisting of an entrance step, providing the barrier and the barrier-less cleavage to the strong electric field, is often considered a state-of-the-art conceptual description. Often, well, only in that one publication, but okay. State-of-the-art conceptual description of the frustrated Lewis pair-mediated hydrogen cleavage, considering the previously published framework, suggesting synergistic donor sigma star and sigma acceptor electron donations as key elements via a computational treatment of 6 FLPs, blah blah blah. So in this paper he wanted to carry out a more detailed analysis of the orbitals and to see, is there really an electric field model necessary to explain this reactivity. So he studied 6 systems, including bridge systems, even this small bridge system, which all of them result in hydrogen splitting, intermolecular, intramolecular. And let's read some of the conclusions. It's a very big paper, a lot of theoretical calculations, a lot of theoretical models, but that's the bottom line that they write here. FLPs with similar reactivity show remarkably different field characteristics. Yeah, so they discover that all of those pairs do react with hydrogen. Some of them supposed to have completely different electric field between the acid and the base and the acid, because of different polarization, different nature of the groups, blah blah blah. They do all those calculations. However, despite those different field characteristics, they still show similar reactivity, in contrast to the suggestion of the electric field model. Strong electric fields are not present in cavities of the FLPs. That's also important. So they say that the strong electric fields, actually, they're not in the cavities, but only in the spherical regions around those complexes. But the reactions actually happen inside those cavities. That's another important thing. So electric field generated by the FLPs in the region of H nuclei, although capable of accounting for some reduction of H2 cleavage barrier, is too small to provide the barrier-less cleavage. Yeah, that's also a very important contradiction with the paper by Grimme and Erker. They say just the energy is not enough. The electric field-based model provides no explanation for the geometry of the transition state, and the hydrogen-hydrogen axis is not oriented parallel to the electric field. Again, that contradicts, right? And so on and so forth. But listen to this. They kind of respond to the a bit offensive comment by the previous group. Computational methods with less satisfactory performance provide somewhat inaccurate transition state geometries, but still they describe the correct electronic events occurring upon FLP H2 activation. That's a very polite answer. While the effects of the electric field are not negligible in the quantitative terms, the quantum nature of these particles, electron transfer via orbital overlaps, has a profound influence of the qualitative behavior. So I think those statements are pretty destructive, to the electric field theory. But that was not the end of the story. 4 years later, in 2017, another group, this time from Belgium, also investigated this topic, comparing those two mechanistic suggestions, the electron transfer and the electric field. And again, this is a very huge paper, very complicated, very long. It was for me a bit hard to read it. I'm not a theoretical chemist, maybe that's why. What they did, they studied again 6 systems. However, they studied also the contact Lewis pairs, those that can make the bond. And they discussed the mechanism of those different systems. The conclusions were very different from Papai's group. What I didn't like there, they didn't really address each of those comments by Professor Papai. They kind of ignored them, but it's like they studied everything from scratch, which is bad, and that's what they write. Our analysis revealed that the widespread reactivity concept, again, widespread, it's not widespread, it's something that was proposed by Professor Papai mostly. Maybe others just repeated it. Anyway, our analysis revealed that the widespread reactivity concept, which explains hydrogen-hydrogen bond breaking by the synchronous electron donation from base to the sigma star of hydrogen and electron withdrawal from the sigma orbital of hydrogen to the acid, is valid for high energy transition states. So they say that there's basically both Professor Papai and Professor Grimme are correct, but for different systems. That's interesting. They say that there's high energy transition states and there's low energy transition states. So for high energy transition states, maybe there is an electron transfer. However, it's too energy demanding. That's why it's for high energy transition states. For low energy transition states, they state that there is still this electric field model, which is correct. So our reservations put forward the critical importance of electrostatic field generated by the acid and base centers in the case of geometrically early low energy transition states. By the way, those common Lewis pairs that everybody studied prior to this publication, yes, it all falls into the low energy thing. So anyway, first, a strong electrostatic field polarizes hydrogen to great extent and accordingly shifts its electron density towards the acid, which blah 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 blah. Anyway, they say the same thing, that the strong electrostatic field, that's what that makes the reaction happen. We provide convincing support for the central role of the electrostatic field in the heterolytic H2 splitting process of FLPs. Convincing. Let's see though, was Professor Popeye convinced? So the next paper by Professor Popeye came 2 years after that, and again he studied similar Lewis pairs. All the hydrogens are in place, very good work, but that was not per se a mechanistic study. That was more about comparison of two models, the static and dynamic model. So he sort of ignored the publication by the Belgian group, but there is a small paragraph in the paper. So he discusses only this mechanism that he originally calculated. And this is the only paragraph when he mentions the electric field mechanism. An alternative reactivity model emphasizes the role of electric field. You see, that not only widely spread, but alternative, okay? Emphasizes the role of electric field created by the active centers of the encounter complex. However, the relevance of this model as a conceptual basis in FLP type H2 activation could be questioned, right? Nevertheless, a recent computational study reiterates the central role of the electric field and the authors claim to provide a unified reactivity concept of the for H2 activation via FLP. Yeah, the authors claim. I mean, that's maybe answered the question which I asked here. Who was convinced? Seemingly, Professor Popeye was not convinced, because the authors claim. That doesn't mean the authors proved. So, okay, seems like he doesn't argue with them too much though, so, okay, so there's two theories, let's leave them behind, but no. In 2023, last year, a new publication appeared, this time from Polish group. And this one is really cool. Three-body interaction effects in the heterolytic hydrogen splitting by frustrated Lewis pairs. So they study basically two systems. One, the same one which everybody studies, but the other one, instead of tertiary butyls, they put the adamantyl groups, which are very big ones, right? And they do a better dispersion of electron from the base. And they do, again, a very detailed analysis. Very deep theoretical paper, hard for me to understand all bits of pieces, but let's see what they write. A large electric field needed to lower the barrier of heterolytic dissociation of hydrogen. The hydrogen would require large values of electrostatic energy between the acid and the base. So he repeats this statement by Professor Popeye, which he did not saw those large values of electrostatic energy. Nothing like this emerged from our analysis. Thus, the pure classical electrostatic model is not supported by our results. Just a step back. So what they say is that when the hydrogen enters the cavity of the complex of base and the acid, something happens. So before that, there's basically no exchange, any effects between the centers. But when the hydrogen enters, then something explodes inside the cavity, right? The three-body effects in both complexes transition states have a significant component of the exchange induction non-additivity and delta HF, higher order reduction, both of which are quantum effects. Again, they say that once hydrogen enters between the donor and acceptor, there is some quantum effects starting happening. Ooh, the magic of quantum effects. We can confirm that the activation of induction does occur when H2 is inserted between the FLPs. Thus, the electron transfer model, suggested by Professor Popeye, acting as a relay, the H2 acting as a relay in electron transfer between the base and the acid, is consistent with our data. Again, polite, right, but solid. So I think this cross here, according to these results at least, is justified. until someone else shows something else. And I especially like this sentence here. So the H2 acts as a relay, so it makes the electron transfer possible. So bottom line, this publication sort of cancels the electric field model and leaves us only with this option. However, again, they ignore here a very important statement by the Belgian group, because they say actually that this electron transfer requires too high energy, and that's why they doubt that it can happen. That's why they look for lower energy options. Allow me to bring here my idea, okay, that how can it be explained? So how come this high energy reaction is possible of electron transfer? I think that there may be some third way once hydrogen enters the cavity between the acid and the base. It makes this complex to be as one molecule, basically. And we know that a common thing in molecules, especially where quantum effects come into work, there can be some chemical resonance effects. And that's what I try to draw here. Okay, so yeah, all the researchers say that there's no charge transfer before the hydrogen enters. But once it enters, I'm not sure we really need to draw the stepwise, like, yeah, electron drops here and the electron drops there. We can just write this resonance structure. You know, it can be just tunneling way. That's what happens in the conjugated molecules. And it seems like here you don't have the conjugation, but I don't think anyone calculated those resonance structures. And there are theoretical ways to calculate those resonance structures. So that's what would be very interesting to see, if the resonance structure can form here. What does it mean? Well, yeah, so basically the electrons exist in both states. Both of them are on the base and zero on acid, and some electron density is also on the acid once the hydrogen enters. And once it happened, the wave function can collapse into the radical pair, right? The ion radical pair. So I write here this entangled radical pair model. Please check my video about those radical pairs. Yeah, this is the video I mean, and I actually explain there why I call those radicals entangled radical pair. And I even wrote it down as a hypothesis and published in a ChemArchive, so you can check up this paper as well. And once the wave function collapses to the d-radical system, this hydrogen splitting is going with a radical mechanism, simultaneous abstraction of hydrogen from one another by each of those radicals. All the links to all the publications are in the description below. I hope you liked this video. Please support Ukraine, which is still tortured by the Russian aggression, and please support a ceasefire in Gaza and the return of the Israeli hostages. Thank you, and see you next time.